If you think back all the way to August this past year, back to step 3, we learned all about the distributive property. In step 16, we're going to learn about factoring the greatest common factor, which is in some ways considered the opposite of the distributive property. We are undoing the distributive property. Instead of starting with an expression like this, we're going to start with something like this without the parentheses and look at the two terms and think, what do they both have in common that we could pull out from each? So for instance, in the first example here, I have a 5x and I have a negative 35. Those are my two terms. What do 5 and 35 have in common? Is there a number I can divide both of them by? And the answer is yes. I can divide them both by 5. If I divide 5x by 5, I'm left with just x. If I divide negative 35 by 5, I'm left with just negative 7. And we're going to do that for each term in our polynomial expression to find what they have in common. Even though we can see the answer here on the left, let's take a look at this example on the right. In my first term, I have 12x squared y squared. In my second term, I have 32xy cubed. So I look and think, what can I divide 12 and 32 by? Well, they're both even. I can divide them by 2, but it's even bigger than 2. I can divide them both by a 4. So I'm going to put 4 out front before the parentheses. Looking at the yellow term and the blue term, the yellow term has 2 factors of x. The blue term only has 1x. So what do they both have? They both have 1x. So I pull out 1x. The yellow term has 2 factors of y. The blue term has 3 factors of y. In other words, the yellow term has 2 yo-yos, the blue term has 3 yo-yos. They both have 2 yo-yos, 2 y's. So we're going to pull out a factor of y squared, 2 factors of y. And again, you can take each term and divide by this greatest common factor that you've pulled out in front of the parentheses. 4xy squared. And reduce. 12 and 4 leaves a 3. X squared on top and x on the bottom leaves a factor of x on top. And the y squareds are gone. So my new yellow term is simply 3x. That's all that's left behind. In the y term, if I divide by 4xy squared, remember that's my greatest common factor, and I reduce, 32 and 4 reduce to just 8. The x's cancel, and all but one y on top cancel out. So I'm left with 8y for my second term. Let's practice a few where we don't have the answer sitting right next to us. Here in the first term, I have 6x squared. My next term, my second term, is negative 24x. So let's think about numbers first. What's the biggest number I can divide both 6 and 24 by? And the answer is 6. In fact, I'm not going to write it there. Let's write it over here. 6. Now let's look at the variables. Let's look at the x. They both have 1x. The yellow term has 2, but they both have 1x. And now I have to write what remains after I factor out 6x as my GCF. Again, if it helps, go ahead and divide by that GCF. and write what remains. But you can also think 6x times what is 6x squared? 6x times x. Negative 24x times, 6x times what is negative 24x? Negative 4. So x is remaining from my first term. Negative 4 remains from my second term. Again, if you look at canceling out by dividing by the greatest common factor, you'll see that you're left with x for the yellow term and negative 4 for the blue term. How about this one? Jumping ahead a few problems. What's the biggest number I can factor out of 17 and 51? The answer is 17. The first term has an x squared, the second term has an x, so they both have 1x. If I divide by 17x, which is my greatest common factor, I'm left with x for the first term, and I'm left with 3 for the second term. And you can check. You can take your answer and distribute, just like we did back in step 3 back in August. If you distribute, you end up with 17x squared plus 51x, which is exactly what we started with in this problem. Let's look at this next one. We have not 2, but 3 distinct terms. We have a yellow term, a blue term, and a pink term, and we're trying to think, what is the biggest number that I can divide into each of these terms? If you know your facts quite well, you'll know that 9 is the biggest number that will divide into 36, 63, and 27. Now let's look at the x variable. The yellow term has 3 factors of x, the blue term has 2, and the pink term has 1. What do they all have? They all have at least 1. And let's write what remains behind. If I divide by 9x, 36 and 9 cancel. 3 x's on top and 1 on bottom cancels and leaves me with 2 on top. So my yellow term becomes 4x squared when I factor out my greatest common factor of 9x. The next term, dividing by 9x, 63 and 9 cancel, and I'm left with 7. 2 factors of x on top and 1 on the bottom leaves me with 7x for my next term. And finally, with the pink term, when I divide by my GCF, the x's cancel, the 9 and 27 cancel, and I'm left with just negative 3. Again, if you were to distribute this 9x, you would end up with 36x to the third plus 63x squared minus 27x, which is exactly what we started with. One thing to remember, if the leading coefficient is negative, you should factor out a negative. For example, in this next problem, negative x squared, 5x, and negative 6. Remember, this is a negative 1 right here before the x. Negative 1, 5, negative 6, they don't have a number in common that we'll divide into them, that we can divide them by. They also don't all have an x. So there's nothing we can factor out, but paying attention to what this says, if the leading coefficient is negative, which it is in this case, we want to factor out a negative. We want to pull out a negative. In other words, we're going to divide each of these by a negative 1. So the negative x squared becomes positive x squared. The positive 5x becomes negative 5x. And the negative 6 becomes a positive 6. This is as simplified as we can go right now. Let's multiply these binomials and look for patterns. If we were to put this into a box, let me get a better box over here. I have enough space to write. There we go. And I have x minus 1, x minus 1. When I multiply, I get x squared minus 1x plus 1. The terms right here, inside and outside terms combine, and I'm left with x squared minus 2x plus 1. The next one, if I box the next one, draw my box, x minus 3, x minus 3. That gives me x squared minus 3x plus 9. Again, the terms with an x combine, and my answer is x squared minus 6x plus 9. So you might be noticing a pattern that when both of our binomial factors are identical and we square them, it's the same as squaring the first term, squaring the last term. Negative 1 times negative 1 is positive 1. And then multiplying them together, negative 1 times x is negative x, and doubling it gives us our middle term. That will work every time you have a binomial times itself. Square the first term, square the last term, then to get the middle term, multiply them together times 2. What if they look very similar, but they have opposite signs? Let's see if we can find a pattern for this. When I box these, x take away 1, x plus 1, I get x squared, negative x, positive x, take away 1. Again, these inner and outer terms combine, and I'm left with x squared minus 1. In other words, it's as if I squared the x and then multiplied the negative 1 and the 1 to get negative 1. So what do we think we would get with this next one? If we follow that pattern, we should have x squared minus, what's 3 times 3? 9. Let's check it with our box method. With the box, I have x take away 3, x plus 3, which gives me x squared minus 3x, positive 3x, and a negative 9. Notice the 3x and the negative 3x cancel out, just like they did in our first example, and we're left with x squared minus 9, which is precisely what we thought we would get. This is a special case scenario. What we have here, we have two terms with a subtraction sign. The first term is a perfect square, the second term is a perfect square, and the subtraction sign means difference. What we have is a difference of squares. Whenever you have a number plus a number times a number minus that same number, you simply square the first number, square the second number, and put a subtraction sign between them. And to go in reverse, if we have an expression that has two terms, the square of a, the square of b, separated by a subtraction sign. In order to factor these, we're simply going to take the square root of a squared, one's a plus, one's a minus, and the square root of 49, which is 7. Notice what we started with today would not have worked here. A squared and 49 do not have any common factor. So we can't just factor out a factor of A or a factor of 7, or they don't have anything in common. But they do have a special property happening where A squared is a perfect square and 49 is a perfect square. P squared is a perfect square. 144 is a perfect square. One's positive, one's negative. The square root of p squared is p. The square root of 144 is 12. Now 144 was a big number. You may not have recognized that that was a perfect square. That's why it's so important to memorize this chart. These numbers down the right are very, very special, important numbers. These are the first 12 perfect squares. 1 squared, 2 squared, 3 squared, 4 squared, and so on, all the way up to 12 squared. These 12 numbers are very special numbers, and when you're factoring, it's important to be able to recognize them and say, oh, look, it's a perfect square. It's one of those special numbers. Let's try another one. K squared, 121. K squared is K times K. 121 is 11 times 11. So I break it into two parentheses multiplied together, two binomials. One's positive, one's negative. K and 11. Sometimes it's going to look a little more complicated, like this example. 4x squared is still a perfect square. 25 is a perfect square. It's 5 times 5. Taking the square root of 25 is easy, so we'll start with that. We know it's going to be plus 5 minus 5. Here, if it was just x squared, we would put an x and an x, but it's not just x squared, it's 4x squared. What times itself gives me 4? And the answer is 2. 2x times 2x is 4x squared. In other words, I'm taking the square root of this number, this term rather. Square root of 4 is 2. Square root of x squared is just x. Right here, we have a perfect square, subtract a perfect square. So I have two parentheses, one's positive, one's negative. The square root of 9 is 3. The square root of a squared is a, 3a. The square root of 4 is 2. And there we have it. Feel free to try a few more of these examples. I will continue to work them out, and they can be found in a binder in room 112 if you'd like to check them. If you have any questions, please feel free to check with your math instructor.